But let's switch to plovers, and let's talk a little bit about these birds. Is it showing? Let's see here. All right. So piping plovers are small migratory shorebirds that were listed under the Endangered Species Act in 1986, following a population decline which was attributed in part to habitat loss, recreational use, and predation. And they occupy 3 breeding subpopulations, so they're listed as endangered in the Great Lakes, and they're threatened in the Great Plains and along the Atlantic coast. They nest on sandy beaches, and their chicks are precocial, meaning that they're up and moving and feeding themselves soon after hatch. And while their wintering locations vary by breeding population, the Atlantic coast population, which is what I will be talking about today, they overwinter from the Carolinas down south through Georgia into Florida and well into the Caribbean. While Atlantic coast plovers also nest on the mainland, they frequently breed on barrier islands. So barrier islands are highly dynamic systems that undergo repeated cycles of disturbance and succession, and they naturally retreat via overwash, which is the landward movement of sand that's caused by storm surge and waves. So in this photo here, you can see an example of an overwash in the middle. Storm surge moved sand towards the bay side of the island, buried vegetation, and created an open expanse of dry sand through the middle portion of the island. So barrier islands provide both ocean and bayside foraging habitats for piping plovers. And studies have shown higher invertebrate densities in low energy bay intertidal habitat compared to higher energy ocean intertidal habitats. So we studied piping plovers on Fire Island and Westhampton Island, New York. These are 2 barrier islands off the southern shore of Long Island, New York. And this area includes developed communities as well as that are made up of federal, state, and county parks, where substantial pedestrian beach use occurs in the form of pedestrian walk-on beach use and off-road vehicle use. And while Fire Island experiences very heavy recreational use, managers across the system protect piping plover nesting habitat at the beginning of each breeding season with symbolic string fencing. So that consists of signage that you can see here that's connected by string, and it designates areas as closed to public use. So again, that includes both pedestrian and off-road vehicle use. Hurricane Sandy reached the Northeast United States in October of 2012, and at the time it was the largest diameter Atlantic hurricane on record. And it brought rain, snow, wind, and extreme storm surge to much of the eastern US. The storm altered Fire and Westhampton Island in a few different ways. So here's an aerial image of Fire Island in April 2005, so many years before Sandy. As you can see here, the island consists of fairly narrow beachfronts with a lot of vegetation and marsh towards the bayside. I'll just point out this reference point here, this dock. And then you can see the same point less than 2 weeks after Hurricane Sandy. So the storm breached Fire and Westhampton Islands like this in a few locations, so creating a new channel from ocean to bay. And it also overwashed the island in many other locations. So you can see that just to the right here where sand has transferred towards the bay. In this case, it reached pretty far towards the bay, but some other overwashes on the island actually reached there on a larger scale and created bay intertidal foraging habitat on the other side of the island. And because these geomorphic changes are said to put the mainland of Long Island at risk to future storm impact, the U.S. Army Corps of Engineers moved fairly quickly to stabilize the islands following the storm. So the Army Corps filled breaches, and they also nourished beaches with dredged sand. And they built dunes above Hurricane Sandy overwashes and planted them with American beach grass for further stabilization. And to mitigate the impact of engineering to the piping plover nesting habitat, the U.S. Army Corps of Engineers also engineered these plover restoration areas. You can see one here. And they were designed to provide dry sand nesting habitat for plovers. They were developed in 2014, so 2 years following Hurricane Sandy, and were available for use in 2015. So in the few years after the storm, these 4 habitats were developed, so I just spoke of these. There are also a few others on the landscape at the time, including manipulated dunes, which were essentially just dunes that were created through the placement of snow fencing and Christmas trees, which allowed sand to accumulate over time, eventually forming dunes. Also beach nourishment, so this is when dredged sand is placed on the beachfront and widens the beach. And then regions of dredged sand stockpiles, which were in a few locations following the storm. So previous studies have illustrated the benefits to piping plovers following large-scale disturbance events and subsequent engineering. And this includes an increase in habitat, increased pair abundance, and then also higher survival rates. So the objectives of this study were to not only evaluate the effects of natural processes, but also the effects of engineering to habitat selection of the piping plover, and also to explore some aspects of plover demography and movement that have remained relatively understudied. So the specific objectives of my thesis, in chapter 1, I looked at nest site selection and suitable nesting habitat. And this included assessing how plovers selected nest sites before and after Hurricane Sandy, quantifying how much suitable nesting habitat existed before and after the storm, and then determining how much suitable habitat was protected from recreational use. In my second chapter, I looked at post-fledging survival and migration. So this included estimating post-fledging survival both on the natal grounds and across the first year, and assessing factors that influence fledgling migration and the probability of second year return. So we'll dive right into chapter 1, looking at nest site selection and suitable nesting habitat. While I will be reviewing this whole work today, if you're interested in more details regarding my first chapter, as Jim said, please check out our paper in Ecosphere, which was published last June. So in order to evaluate nest site selection before and after the storm, we had to establish 2 years that we selected based on data availability. So our pre-Hurricane Sandy year was 2010, and our post-Hurricane Sandy year was 2015. In 2010, we were not on Fire Island doing any study, so we obtained nest coordinates from the Fish and Wildlife Service, and then we collected our own nest data in 2015. So in 2015, we searched for nests every 1 to 3 days, and we collected trimble locations of each nest. We also mapped the spring high tide lines to determine the ocean and bayside limits of usable nesting habitat. And we walked the boundaries of pre-nesting, symbolic fencing, again with that Trimble GPS unit. We obtained aerial imagery from New York State in 2010, and we had imagery flown in 2015. Both of these were 15-centimeter resolution, so pretty fine scale imagery. To give you a sense of that, here's how a pixel from this imagery would fall above a piping plover nest. And we used a supervised classification in ArcGIS. So we classified each 15-centimeter pixel into one of 4 habitat categories. So these were dry sand, wet sand, vegetation, and water. And then we clipped these classifications to the spring high tide line, assuming that nests cannot complete a full incubation cycle without being flooded by a spring high tide. So essentially we didn't include that as being available nesting habitat. And we used the imagery and classifications to derive predictor variables in ArcGIS. We hypothesized that a number of geomorphic variables would influence nest site selection, These included elevation, backshore width, which is the perpendicular distance from the spring high tide line to any sort of back beach barrier, which is anything from dense vegetation to a high dune. The amount of surrounding vegetation, distance to development, and then distance to both ocean and distance to bay. So we looked at these from a Euclidean standpoint. So a Euclidean distance, which accounts for how an adult would fly to reach both of those foraging habitats. And we also looked at a least cost distance. So this accounts for how a chick would walk, assuming that they cannot traverse through a 15 centimeter classified pixel of vegetation or water. For each year, we created random points that we confined to dry sand, and then we modeled nest site selection using logistic regression with additive variables and an interactive effective year. And we excluded the least biologically relevant variables if any were correlated. In order to produce the best fitting model of plover habitat use, we selected the full model for future inference. So here are results for 2010. I will walk you through this graph. On the x-axis, we have standardized beta estimates and 95% confidence intervals. And on the y, we have all the variables of interest. So if any of these point estimates and error is to the right of this line at 0, that indicates a positive association with nest site selection. And if it's to the left, it indicates a negative one. So the major results here, least cost distance to ocean was the best predictor in 2010, had a strong positive relationship with nest site selection. So this means that birds were selecting nest sites that were actually farther from the ocean than we would expect at random, which at the time likely reduced the probability of tidal flooding of nests. We also found that nest site selection was positively associated to distance to bay. So both as a chick would walk and as an adult would fly. So birds were selecting nest sites far from the bay. And this is likely a function of most of those regions that were far from the ocean to avoid flooding were actually within the middle, wider portions of the island in 2010. And there really wasn't a lot of bay access except for at the inlets during this time. And now we can look at the difference between 2010 and 2015. So again, we have standardized beta estimates and 95% confidence intervals and the same variables of interest. And you'll note that nest site selection has now shifted. So least cost distance to bay was heavily driving nest site selection in 2015. So plovers were selecting nest sites close to the bay as their chicks would walk, and also close to the ocean as their chicks would walk. So essentially they were balancing themselves in the middle of these Hurricane Sandy overwashes. And using these results, we modeled all dry sand for suitability in both 2010 and 2015. We established a suitable threshold at 0.5, at which the model had the highest percentage of both nests and random points correctly classified. And then using both of these imageries, we created a probability map like the one you see here. So any pixels with a probability above our threshold were considered to be suitable habitat, and anything below was deemed unsuitable. Once again, you can see just how this map is cut by that spring high tide line. And here's a representation of how this suitability threshold played out in one section of our study area. So this is Smith Point County Park. So up top here we have 2010, and on the bottom is 2015. Suitable habitats in red, unsuitable is in blue. And then once again, you can see how that spring high tide line played a role in both of these years, more so in 2015. The main takeaway here is these the increase in red. So we see these large areas of red on the bottom in 2015. These were both overwashes, but we were interested in quantifying this. So as you may recall, we have a number of habitat categories across the study area. So we wanted to quantify suitable dry sand across each of these categories in each year. And the only habitat that existed in 2010 we called other. So other is essentially any dry sand that was not overwashed during Hurricane Sandy, nor was it engineered upon following the storm. So essentially everything fell within this other category in 2010. And then we compared this to all of the 8 categories that were available in 2015. So all those 7 that I already mentioned, and then other as well. And using ArcGIS, we designated all suitable dry sand into one of these 8 categories. So for our estimates, we categorized suitable sand into the most recent habitat category, and no dry sand pixel was counted twice. So here are the results of that. So all of the habitat categories are on the x-axis here, and suitable hectares on the y. The year 2010 is in gray, and everything in teal is 2015. So the main takeaway here is the total. We went from 100 hectares of suitable nesting habitat in 2010 to 250 in 2015. So this is a 1.5-fold increase in suitable nesting habitat. You'll also note how storm overwash provided over 60 hectares of suitable habitat for plovers compared to all of the other engineering types, which didn't amount to this much. But we can't really deny this other category, right? So as I said, everything in 2010 we considered other, but in 2015 there were over 130 hectares of this other suitable habitat. So what does that look like? And here is what some of that looks like. So we're interested in looking at how much suitable habitat was protected from public use. So we assessed how much was within the bounds of the symbolic fencing early in the season when birds arrived to start nesting. And we found that only 58% of that suitable nesting habitat was protected from public use in 2015, and that plovers were nesting within these protected areas more often than we would expect if they were selecting nest sites randomly. So 96% of the nests from 2015 to 2017 were within these symbolically fenced areas. Here's a depiction of that. You can see these nests in blue, all the suitable habitat in red, and then these hatched regions are what's protected by symbolic fencing. And really this just illustrates the importance of symbolic fencing to making geomorphically suitable habitat actually functionally available for piping plovers. All right, so now I'm going to switch gears a bit and head into my second chapter, in which I assessed post-fledging survival and migration. So the annual cycle of the piping plover is usually viewed from a breeding season standpoint. The breeding season starts in early April when most adults return to their breeding grounds and start establishing territories. Anywhere from April to June, plovers are initiating nests, and then those chicks hatch just about a month later. Nearly a month after that, birds begin to fly, so they fledge from July to August. And then as early as July, birds embark on southbound migration. They're overwintering, and then they migrate north once again to start the process all over again. And since federal listing, population monitoring and banding projects have enabled a greater understanding of the demographic processes that contribute to population growth. Throughout the annual cycle, studies have generally focused on demographic rates during the breeding season, ones that pertain to the breeding season like adult survival, nest survival, and chick survival. However, the stages from first flight through migration and wintering are generally understudied. And so in order to ask research questions about this time period, this part of the annual cycle should be further divided into stages and viewed through a slightly different lens. So instead we can view this time period like this. So again, chicks are fledging roughly July through August. They're embarking on that southbound migration. They're overwintering roughly from November to January. They're coming back north. And then some second-year birds may be breeding in their second year from April to July. And because population growth is ultimately influenced by breeders, and the breeding population is partially made up of second-year returning birds, it's important for us to understand the factors that influence first-year survival, as well as the time spent persisting on the natal grounds and on the non-breeding grounds prior to those really crucial first-year migrations. So we aim to fill some of these knowledge gaps to improve our understanding of that first year following fledge. And there are a number of factors that could be influencing post-fledging survival. So fledglings may be particularly susceptible to depredation immediately following fledge because they're no longer defended by their parents. We expected lower survival during this initial period of post-fledging independence due to predation risks while being accustomed to flight, while becoming accustomed to flight on the natal grounds. Compared to ocean beaches, bay intertidal areas provide higher quality brood rearing habitat and they yield higher chick survival. Thus, we expected that natal habitat might carry over to influence fledgling survival. And also body mass, which is a relatively good index of body condition, is known to influence juvenile survival in birds. So we expected the same might be true for plovers. Given that chicks that hatch earlier in the season typically have higher survival, we expected the same trend could be true in fledglings. And then as fledglings begin to embark on migration, they may experience higher mortality during energetically demanding migratory and wintering months. And finally, we also hypothesized that there could be yearly differences in survival due to extrinsic factors such as large-scale weather events. And looking at post-fledging migration, we also expected that some of these factors like natal habitat type, body condition, fledge date, and year might influence the onset of fall migration. So to address these questions, we surveyed all of our study area twice a week from April through August or September from 2013 to 2019. And all of our breeding birds have been banded since 2013. So every year following our April return, we resighted those banded adults, we located nests, and we monitored nests until hatch. Immediately following hatch, we marked each chick with a uniquely identifiable alphanumeric green flag and an orange band combination. And we attempted to resight broods every 1 to 3 days. And we resighted individual chicks when possible. So upon resight, we noted the habitat that each chick was in, such as ocean, bay, or inlet. And then during 2015 to 2018, we recaptured chicks with butterfly nets just before they could fly, so around 20 to 23 days. Once recaptured, we aged each chick and then we took a measurement of pre-fledging mass. In hopes of identifying specific sources of natal ground mortalities, in 2017 and 2018, we affixed nanotags to a sample of fledglings during recapture. So if we recaptured more than 2 chicks per brood, we randomly selected individuals to receive a tag. And we glued these nanotags to the interscapular region of the back, so on the base of the feather shafts or the bare skin. And then we glued the feathers on top of that tag to add a little more security. So we surveyed for all of our fledglings, banded and nanotagged, twice a week until the end of August or September, depending on the year. And we searched for nanotag fledglings every 1 to 3 days with a handheld receiver that you can see here. Upon detection of a signal, we tracked it until we could confirm either a live bird with a visible nanotag, a dropped nanotag, a dead bird or a mortality location, or a live but unseen bird whose nanotag signal changes were consistent with typical plover behavior. Beyond our study area, we received resite data from auxiliary reciters, many of which were opportunistic from birders along the coast, but resites also came from individuals and or organizations that were conducting similar breeding surveys to us, where we were regularly searching for birds. They also came from some migratory stopover locations where these surveys occurred during some years of our study. And then also from wintering locations. Here you can see the lovely Bahamas. So given the use of nanotags and banding, we assess post-fledging survival using two different methods. So using radiotelemetry, we estimated natal ground survival with the Mayfield method, which essentially derives an estimate by dividing the total number of days that a bird survived by the total number that they held a nanotag. So that includes both survival and mortality days. And to gain a better understanding of how long these nanotags were being retained and any factors that could be influencing retention, we used a logistic exposure model. So logistic exposure models are similar to logistic regression, but they allow for the exposure periods, or in our case, the time between observing fledglings. They allow for those periods to vary. So we modeled the effect of a number of factors on retention. And we used a multi-state open robust design model to estimate survival, detection probability, and state transition probability of fledglings from July 1st of their hatch year to July 1st of their second year. And while these models can estimate other parameters, I'll only be focusing on these three today. So robust design models enable precise parameter estimation even when sampling is opportunistic, which makes it very ideal for the use of plover migration and wintering data, again, where that resiting is often performed by the public. So robust design models also enable the use of primary sampling periods that are made up of multiple secondary periods. So here is the setup of this model. I'm really not going to dive too deep into methodology, but the takeaway here is that the primary periods changed according, the lengths of those primary periods changed according to the time of year. So from July 1st to August 23rd, when we were on our breeding area surveying every 1 to 3 days, the primary periods were 9 days long, and they consisted of 3 3-day secondary periods. We transitioned to 30-day primaries when we weren't conducting these regular surveys, and then we moved back to 9-day primary periods when we returned to the breeding season in April the next year. We defined 3 states within the annual cycle. So these were post-fledging, migratory wintering, and return north. A fledgling was in the post-fledging state if they were still within the bounds of the Fire Island study area within their hatch year. They moved to the migratory wintering state once they left Fire Island. And because some Fire Island fledglings may emigrate and breed elsewhere in their second year, our 3rd state was a return from the non-breeding grounds. So North Carolina marks the northernmost wintering range of piping plovers. Therefore, we considered fledglings to be within the return state once they were seen north of North Carolina in their second year. So this state was a combination of migrating birds, prospecting birds, and breeding birds. And looking at these 3 states, we were interested in just 2 transition probabilities, the only 2 that were possible. So this was migration probability and return probability. And we tested the influence of covariates on survival, detection, and transition parameters based on the a priori hypotheses that I spoke of earlier. So we modeled survival and migration by time, state, year, pre-fledging mass, natal habitat type, and fledge date. Return probability by time, state, and year, and detection by time and state. All right, so let's dive into some results. We deployed nanotags on 43 fledglings. 33 individuals dropped their nanotags, and 3 of those fledglings died. 2 mortalities resulted from avian depredation. 1 was confirmed to be a great horned owl, and the other was suspected to be a raptor based on the presence of the nanotag in a pile of plucked feathers. The 3rd mortality was a result of dehydration that was confirmed by a necropsy. And we found daily survival of nanotagged fledglings to be 0.997, so pretty high. The question is, how long were individuals surviving at this rate? So we looked at retention, right? The strongest predictor of nanotag retention was days since tagging. So predicted nanotag retention decreased as days since tagging increased. And retention was higher in 2017 than it was in 2018. The average retention was 16 days, plus or minus 10 days standard deviation. So these birds were holding on to their nanotags for about 1 to 3 weeks. As we look at the number of banded birds, we had 292 chicks fledge from 2013 to 2018. And of these individuals, we collected just under 6,500 resites of those fledglings within their first year. While we did test the influence of a number of factors on post-fledging survival, again from July 1 to July 1, none of them explain the variation within our data set. So we found that daily survival was constant across years and across the natal grounds, migratory and wintering, and return states within an individual's first year following fledge. And this daily survival rate was the same, again, with both the radiotelemetry analysis and this robust design analysis. We found that first year survival was 0.36, so this is within range, but on the lower end of previous estimates of post-fledging true survival, which there have been a few. Our study did vary from these studies in that it was the first one to directly assess post-fledging survival across a 12-month period and also test for the effect of covariates on post-fledging survival. All right, let's move into migration. So I'll walk you through this figure here. On the x-axis, we have the primary periods that we looked at from July 1st to September 22nd. And on the y-axis, we have transition probability. We're just going to be looking at migration. So this is fall migration to start. So we found that fledglings were migrating from July 1st to September 22nd. Perhaps you'll note that this last value here doesn't have any error associated with it. That's because we fixed this to 1 because there were no resites of fledglings on Fire Island after September 22nd. So we didn't estimate this value. So 100% of all of our fledglings had to have migrated by this time. Most fledglings departed Fire Island in mid-August, as you can see here, with the biggest migration pulse occurring between August 6th and August 23rd. And migration probability was a function of fledge date, such that the probability of migrating was higher for individuals that fledged at earlier dates. So here again, we have those primary periods on the x-axis, migration probability on the y, and then birds that fledged on July 2nd in yellow, on July 14th in green, and on July 26th in red. And as you can see, by August 15th to 23rd, so this last primary period, migration probability reached nearly 1 for individuals that fledged on July 2nd, but was still around 0.86 for those that had fledged on July 26th. As we move back to this, this figure here, we are tacking on second year return. So second year return probability occurred across 4 primary periods. So it was fixed at 1 by May 8th. So we estimated it across 3 periods. You can see that return probability increased relatively consistently across these primary periods from February 20th to May 8th, with the largest increase occurring in late April. And as we look at both of these migrations together, it's important to note that while on first glance, this figure looks as though fall migration occurs over a longer period of time, that's just the difference in primary period lengths. So both of these migrations actually occurred at comparable lengths of time, 84 days and 78 days respectively. And the greatest increases in migration probabilities occurred over 18-day periods, with the largest transition pulse occurring in the fall here on the left compared to the spring. So our findings that fledglings depart from mid to late August and September is notable given that a few other studies have looked at migration departure and stopover timing in piping plovers. So Loring and others found that piping plover adults departed their breeding grounds in Massachusetts and Rhode Island from July 19th to July 29th. And other studies have shown migratory stopover peaks in North Carolina from late July to early August, and as early as July 10th in South Carolina. So that these stopover findings more closely match the findings in adult departure compared to fledgling departure suggests that fledglings are either stopping elsewhere along migration, that they are less numerous than adults, or that they are departing later than adults. And while it's likely a combination of all 3 of these things, the latter is consistent with other shorebird studies that have found adults to dominate earlier migration counts and juveniles to migrate later. So fledglings persisted on Fire Island for over a month before they migrated, and our results suggest that migration is a function of time since fledging. And while we can't pinpoint the mechanism behind this, it's likely that fledglings require a consistent developmental time. So departure may be delayed to allow time for knowledge acquisition about foraging habitats, about flight, or about just learning about local surroundings. Understanding plover migration timing is crucial to properly managing and protecting habitat for young birds before they migrate. So fledglings are persisting on Fire Island until August and September, yet beaches are reopened to pedestrian and off-road vehicle use from as early as June and August in some years of our study. And typically managers reopen popular areas once they're able to confirm broods as fledged. So that's actually the marker for opening areas in some regions. So that's an important thing to note. And given that human use corresponds to lower shorebird use and lower survival, this is concerning for fledglings across a variety of behaviors. So during this time, fledglings are foraging, they're fueling up for their first migration, they're roosting, and they may be prospecting for future nest locations. So extending plover closure dates could protect fledglings across a number of essential pre-migratory behaviors. All right, in summary, the influence of Hurricane Sandy and subsequent coastal engineering projects to both Fire and West Hampton Island, New York, provided an opportunity to assess multiple aspects of piping plover ecology. So in chapter 1, we looked at nest site selection and suitable habitat. I found that plovers selected for Hurricane Sandy overwashes with both bay and ocean proximity. Suitable nesting habitat increased 150% following Hurricane Sandy, but only 58% of that nesting habitat was protected from recreational use. In chapter 2, I found that post-fledging survival was constant across the first year after fledging. That fledgling migration peaked during late August, with birds persisting on those Fire Island natal grounds for more than a month before they migrated. And return from non-breeding peaked during late April to early May. Since Hurricane Sandy, the Fire Island plovers have experienced a 186% population increase. That includes 2019. And so there's no evidence that this population has reached carrying capacity just yet. And so we encourage the use of fledgling departure dates in future habitat management through the end of the plover season in order to minimize the negative influences of beach recreation to piping plovers. While the mortality risk of fledglings on Fire Island is currently no different than on within other stages of their first year, this may very well change as the population approaches carrying capacity. So if the population continues to increase and fledgling production follows, and then vegetation succession continues, density-dependent effects like competition and predation may begin to negatively influence fledgling survival and how long they're persisting on Fire Island. In the face of future storms and geomorphic change, the targeted conservation of both storm-created and engineered plover habitats should be implemented early in the breeding season and then follow through until fledglings depart, to maximize the benefits of suitable habitat across all breeding stages to improve the conservation of the species. So I have so many people to thank for this work. I would just first off like to thank our funders, so the U.S. Army Corps of Engineers and the Fish and Wildlife Service, to all of the collaborating agencies that we work with on a daily and weekly basis. This is such a collaborative effort, and thank you so much to our field technicians over the years, to Pam Loring and Peter Payton, who really helped me get started with this nanotag work back in 2017, to the many, many reciters who have contributed to this analysis now. Thank you so much. It couldn't have been done without you. To everyone in the Fish and Wildlife Department, FIGSWA, all the administrative staff, thank you guys so much. It's been a blast, and I again, couldn't have done this without you. To the Graduate School, Graduate Student Association, and to the Shorebird Program. I also have many more people to thank, so bear with me. I have to give a very special thanks to my two advisors, Dr. Jim Fraser and Dr. Dan Catlin, and also to my committee member, Dr. Sarah Carpentry. I'm so appreciative of everything that you three have taught me over the years. There was once a time when I thought I could never make it in grad school, but each of you have shown me in very different ways something that proved to me that I could. So I thank you so much. To the rest of my lab, past and present, you guys are the best. I have learned so much from each of you. Thank you for the laughs and the camaraderie and all the mountain bike rides. To my fellow Fire Island grad students, these ladies, Hen, Kat, and Sam, I couldn't have imagined doing this with anyone else. And I have to really special shout out to Sam, who has more or less been my rock these last few years, just a wonderful partner in plovering. I'm so thankful for you as a colleague and a friend. There's more. Huge shout out to the crews from 2017 to 2019, who I worked with personally. This work could not have been possible without you. And a very special thanks to Cam Robertson and Lauren Granger, who were with me for all 3 years of field work in Fire Island. Thank you for keeping me sane on very long field days and through longer field seasons. There's still more. To my roommates, Cedar and Chelsea, who are downstairs. Cedar didn't bark through this whole thing, as far as I heard, so that was very successful. I don't know how you put up with me, but I'm so very appreciative. It's been a really wonderful few years of bike rides and plane rides and high fives and lots of Cedar snuggles. And finally, last but not least, to the rest of my beautiful friends and family, thank you for putting up with me, moving all the time and dropping into your daily lives unexpectedly when I got a random day off. I love you all so much, and I thank you for your support. And with that, I will I hope these videos come through. We'll play some videos for you, and I will take any questions through the chat, hopefully, if it works out. Thanks, guys. I guess I'll show my face too. Okay, I just have 5 minutes for questions. Let's see what I got here. How often could you read the unique ID on resightings? Was there a correlation between chick size at hatching and banding and chick size at recapture? The correlation thing, it wasn't something we looked at in this study, but we did pretty successfully read the unique IDs upon observation of the broods. It really was just dependent on how close we could get. As I said, there's a lot of other disturbance around, so we never really wanted to add any additional disturbance to the brood. So we're pretty good at reading the bands, I will say that, so as often as we could, but I can't really give you a specific answer there. Oh, Dean, would bay and ocean proximity be inversely correlated, and could that confound your model? They weren't. So I don't know if you're speaking of 2010 or 2015, which might make a difference, but we did look at those, the correlation between all of our variables, and they were not correlated that highly. So the distance to ocean as a Euclidean distance and the distance to bay, Euclidean distance to ocean and least cost distance to ocean were heavily correlated. So we only included the least cost to account for chick movement, but those were the only two that were correlated in that way. What app did I use and what tools did I use to make my presentation? I just used PowerPoint, and I have to thank my lab for this because they taught me to be very, I don't know, care a lot, I guess, about presentations. I probably spent way too long doing this, but I thank you. I'm glad the rural internet handled the videos. That's good to hear. Hi, Elaine. Were any of the nanotags picked up by towers in the MODIS network? That's a great question. We did initially anticipate to have this be a bit of a migratory study with the nanotags. There is one tower on Fire Island which did pick up a handful of our birds, but wasn't too informative in terms of when they were moving. Let's see, there was one in the Bahamas that got picked up, and that was, and I think one in New Jersey, but it was very limited, lots of errors in terms of getting picked up in Quebec and whatnot. So we didn't really use those data for anything, but I do think it was because retention was so low and birds just couldn't retain them through migration. All right, given your dramatic increase under current circumstances, couldn't beachgoers argue that the earlier opening isn't a problem and no reason to shut beaches down until post-migration? That's a great question. And, you know, our survival estimates show that there may not be an effect of beachgoers on survival by any means. But as I said, the population has been increasing. So all the habitat that was created by Sandy kind of opened things up for the population to take off and increase carrying capacity in that way. So there's a very good chance that as the population does continue to increase, it could be more and more of a problem. And also these sorts of beach closings also benefit migratory shorebirds, they benefit plover adults. So it's a wide-ranging management that can benefit many birds in different life stages. And I just think that it's probably something that should be investigated going forwards, so that we have a feel for at certain population sizes, how is beach recreation affecting them. Thanks. Does anyone else? I guess it's 11. This is such an interesting way of doing things. Thanks everyone so much for tuning in.
Yes, thank you all for coming, and I do appreciate it. And I think we ought to do this. It's such a good way to be to socialize given our isolation. I think Katie has offered to give this talk every Friday from now on.
Yeah, Friday night happy hour is next. How about that?
Anyway, thanks all for participating. I appreciate it. And,
thank you all.
See you at the end.